Now we can define what is called as an intrinsic impedance, which is we define just like how you have R equal to V over I by Ohm's law, I equal to V equal to IR, and R is the resistance. Similar to this, we can define for a plane wave the magnitude of electric field over the magnitude of magnetic field. Electric field is in volts per meter, magnetic field is in amperes per meter. So if I take this over this is going to be something like volt. The units will be volt over ampere, and this is impedance, which is ohms. So that ohms is how much is that resistance. That intrinsic impedance of a plane wave is defined as the magnitude of electric field over the magnitude of magnetic field, which is omega mu over k. Because here clearly you can see that HOY is k over mu omega. But if you use E naught x, so if I take E naught x over this HOY term, then I will get omega mu over k, omega mu over k. So the intrinsic impedance is going to be omega mu over k, which I can replace it with omega and mu, and the diff can be either in terms of the phase velocity, or can be in terms of omega, or it can be in terms of the material properties, which is square root of mu over epsilon. That for free space, right? For free space or vacuum, you see that epsilon naught is this, mu naught is this. If you were to find what is the intrinsic impedance of free space, we go and substitute those values, you will get the value to be 377 ohms. So the intrinsic impedance of the space around us is 377 ohms. So if I were to find the magnetic electric field in space here, and if I find the magnetic field in the space here, if I take the ratio of electric field to the magnetic field, it will exactly be 377 ohms by nature. Yeah. And the phase velocity is going to be 3 × 10⁸ meters per second. So in one case, it's square root of mu or epsilon is eta, and Vp is 1 over square root of mu epsilon. That's the difference between the two. So this is for a general spectrum. We see that the intrinsic impedance is going to be that of free space scaled by this parameter, and the Vp is going to be C over square root of epsilon r mu r. And that's why I always tell Vp is going to be less than C, because this value is going to be greater than 1. 1 over that value will be less than 1, and so Vp is going to be less than C. Let's take two different mediums now. Let's take two different mediums having epsilon r, which is different. In case A, it's going to be epsilon r A mu r A. In case B, it's going to be epsilon r B mu r B. So case A is mu r A and epsilon r A. Case B is mu r B and epsilon r B. Two different mediums. Turns out when I have two different mediums, the frequency in both the mediums are the same. The frequency is the same. The phase velocity is different and the wavelength is different. We know that Vp is equal to F times lambda. The frequency is the same in all the mediums. The Vp is going to be different because it depends on epsilon r mu r ma. If this guy is changing, then what changes is lambda. The frequency is the same. That means if I send a 2.4 gigahertz wireless Wi-Fi signal from the access point, if it passes through a wooden material, you are behind the wood or you are behind the concrete wall, the frequency does not change. It is still 2.4 gigahertz. The spectrum, 2.4 gigahertz spectrum of the Wi-Fi signal is still 2.4. So it does not change. What really changes on wood is the phase velocity Vp, which is going to be less than C. And because of that, the lambda, if Vp is less and frequency is the same, then the lambda has to decrease as well. The wavelength decreases. The Vp decreases and the lambda decreases. So the wavelength in material A, and this is the wavelength in material B, the frequencies are the same, F is the same, but what is different is the phase velocities. These are different. So because of that, the wavelengths are different. I'll show that in this animation here. When there are two different mediums, here you can see that the wavelength is 1 meter. That means from one tip to the other tip at any instance, it will be exactly 1 meter. Whereas here, the wavelength is smaller. It is only 0.75. It is somewhere here, 0.75. So you see that this is going to be a denser medium, meaning that the wavelength is smaller, which means the VPB is lower than VPA. You see that this guy is traveling faster than this guy. This guy is traveling slower because the wavelength is smaller. But notice that this black dot here and this black circle here, the black circles here, they go up and down at the same frequency. That's why in both the cases, F is same. The frequency is the same.